Welcome everybody to this year's CAV workshop virtual lab tour. And I'm very pleased to introduce this year's lab tour leader, and that's Dr. Michelle Vigent of the graduate program in acoustics. And she's got this really neat facility that allows her to replicate what it's like to sit inside pretty much any acoustic environment you can think of, but you're actually inside an anechoic room with a bunch of loudspeakers in it. And so she'll walk through how all of that works. And I'm very pleased that we've got a few of our international liaisons online that are doing not exactly the same, but certainly similar research in sound reproduction. So I'm hoping at the end of this, we can have a nice discussion about different methods and concepts. So Michelle, take it away.
Thank you, Steve, for the introduction. So today's presentation has two parts. The first part is to talk about the AURAS facility, the Auralization and Reproduction of Acoustic Sound Fields facility that Steve just introduced. So we'll go into a bit of the history, reconstruction of it, which happened in 2012 and 2013, and about the details of the hardware and signal processing. And then I'll give an update on a couple of projects that we've been doing in the research group. So to kick things off, there is a video that perhaps some of you have viewed already, but maybe some of you haven't. Hopefully it won't be too laggy. Kelly, if you could please play the video. AURAS is the lab that we have on campus, and AURAS stands for the Auralization and Reproduction of Acoustic Sound Fields. And so we use this facility to reproduce three-dimensional sound fields, such as from concert halls or open offices. And it consists of one central listener location in an anechoic chamber with 30 loudspeakers surrounding it, in addition to 2 subwoofers. This lab is unique. It's really one of only a few in the world that has this type of ability to reproduce sound fields with the degree of accuracy that we have. We use a technique called ambisonics, and specifically we use third-order ambisonics, which allows for a physical recreation of the sound field so that we can reproduce sound coming from the correct directions at the correct time accurately. The methods we use for sound perception studies are typically we have one person come in at a time and they will rate different sound fields, whether those are different concert halls, open office environments, or aircraft noise. The concert hall measurements, the way that we play those or render them for subjects is that we take measurements that are made with a spherical microphone array that capture the three-dimensional sound field. This is called measuring a room impulse response. Once we have that measurement, we then need to mix it or convolve it with a short musical recording. And these musical recordings are made in an anechoic environment, the same as the AURAS facility, so that the music doesn't contain any reflections, and so that when we play back the sound, it is just truly the sound of a particular concert hall. It's important to know how sound is perceived in spaces, both in terms of interior spaces and outdoors. In interior spaces, by knowing how people perceive sound, if they like certain sound fields, for example, we use different spaces for music versus speech. By understanding the perception, we can better design those spaces. In terms of sound perception from outdoor noise, for example, aircraft or road traffic noise, we need to know how annoying that is to individuals so that when regulatory bodies come into play to set limits on how much noise can be emitted from aircraft or how many takeoffs, that sort of thing, we need to understand that perception, the psychoacoustics aspect to what's actually happening in the sound. I found it very beneficial in the past to have collaborations, since it allows the opportunity to work with people with different backgrounds and different perspectives so that the problem that's being evaluated can be looked at from many different angles. And so I'm very interested in doing future collaboration with industry where we can use this facility to reproduce all kinds of sound fields, whether indoor or outdoor sound fields, to really get a sense of people's perception, people's preferences to different products, and see if people like them, find them annoying, or whatever the end target is to achieve the sound signature that the manufacturer would like to have. Great, thank you, Kelly, for showing the video. So I will begin with slides then. So hopefully it was not too laggy. The
link can be provided. Kelly, if you could put that in the chat for people's reference if they want to view it afterwards. All right, so thank you. Our general approach, so for those of you not in this field of research, the general approach that we have is we're talking about some sort of physical space that we're trying to first quantify with measurements. We'll talk about room impulse responses in a bit. So we have some sort of physical environment that we can then measure and then calculate from an impulse response different metrics. This is an example showing reverberation time, the time for sound to decay 60 decibels. We use these quantities in order to predict into the subjective domain of the response of individuals. And in order to obtain that, we have to do subjective studies where we ask people to listen to different sound fields. They give us their responses, and then we try to correlate those with metrics to then be able to have design guidelines to achieve spaces that have what we would call a quote good or ideal as possible acoustics. So in order to do this relation between the objective domain and the subjective domain, we need some sort of test facility, and we can also do these kinds of tests over headphones, but there are advantages to that in that that's a simpler type of equipment needed. Disadvantages are that we may not get the spatial accuracy with headphones that we can with a loudspeaker array. So as I mentioned in the introduction, the presentation is divided into two parts. The primary part of the presentation is to discuss this laboratory facility that we have on campus and how it works, and then some research updates on one or two topics depending on timing. So the auralization and reproduction of acoustic sound fields facility is used for reproducing 3D sound fields. We use the method of ambisonics as mentioned in the video, and we'll talk about that shortly. The facility has 30 two-way loudspeakers, and they're arranged in 4 rings. The central position we've labeled as 0 degrees. So we have 8 rings below, 12 at the ear height, 8 above at 30 degrees, and 2 at nearly overhead at plus 60 degrees. And we also have 2 subwoofers for low frequency reproduction. The facility was originally constructed under the direction of Dr. Weng Cheng Chen in '97. So prior to that, I believe in the '70s, the reverberation chamber had been constructed. And then in the late '90s, there was a desire to build a facility to have an anechoic termination. And this was initially a project sponsored by Boeing to look at transmission loss of fuselage. So this window here, it was where we can do transmission loss testing between the two facilities. The facility, though, was in some need of being reconstructed with some limitations that were found. One of the, Paul Bosch, who worked with Steve Hambrick, had done a series of transmission loss measurements using that window and found that there was poor sound isolation of the anechoic chamber. So this is a view of the original chamber with all the wedges removed. You can see along this part here below these 3 lights that there is some probably MDF or something that encloses it, but actually the ceiling and parts of the walls were actually not enclosed. So the only barrier between this and the adjacent space were the wedges. The geometry was also non-uniform. Originally, I believe it was more uniform, but then due to renovations needed in the space for air ducts, there were actually changes. And so while this was the original footprint, which is larger than what the new chamber is, the reason we had to reduce this front, well, I wanted something that was more uniform here at the front, and then along the bottom here and along the back of the facility, there were some ceiling constraints. So in order to have a uniform ceiling height, this was the new dimensions that we settled on. And these dimensions here are tip to tip dimensions, so not including the 18 inches for wedges. So we improved the sound isolation with the wood stud insulated walls. We'll see this again shortly. The geometry became uniform, and it also opened up some space in the room for a workstation. We also have a cable pass-through now with that's reasonably isolated. And acknowledgements, I would like to acknowledge Dr. George Lacerte, former director of CAV in the aerospace department, who provided a lot of financial support for this reconstruction, and Mr. Rick All, who led and coordinated the construction, and a number of students that worked on the project. So briefly a bit more, here's some view of the base. So it is not spring isolated, but it is raised from the floor. And here's a view of the walls. This was the design that we settled on. Plywood, 3 inches of fiberglass, 2x4 wood studs, and resilient channels to improve the sound isolation. And careful attention was paid during the construction to make sure that these did not get short-circuited. So we have our completed semi-anechoic chamber shown here. It is a semi-anechoic chamber. When we do our subjective tests and other measurements, we are able to place wedges to cover most of the floor to achieve approximately full anechoic conditions. We did free field measurements and found that we can achieve free field down to about the 200 Hertz, 1/3 octave band. And here are those dimensions shown again. And as I mentioned, those are the tip-to-tip open space that we have. And the wedges are 18 inches deep. So the loudspeaker array, we did construct these loudspeakers. And so they have the 1-inch tweeters and 4-inch mid-bass drivers. We tested a few before finalizing these. We did measurements of these in the larger anechoic chamber in AURAL's water tunnel facility and created filters for each of them. Later, we created 2 subwoofers with 18-inch drivers, and they are relatively large. We needed these for a project using a type of supersonic flight called Mach Cutoff, which I will talk about in the second half of the presentation. To show you the response of these, we're able to, so the faint recording, which is a recording of a supersonic maneuver, and then our reproduction capabilities for it, you can see that the orange we do relatively well down to approximately 15 Hertz or 13, 12 Hertz, and then it's difficult to have enough of that infrasound energy in the facility. The hardware that we use, once we process the signals, which is what we'll talk about in a moment, we can then send these out. We have an RME, which is a USB to multi-channel digital output, which sends it to this device here that can output up to 32 channels. The loudspeakers are passive, so we have amplifiers for them. And then they're all connected through this pass-through, and then we have the chamber where a person can sit in the middle, as you saw, and answer questions about different sound fields presented to them. The way that we can reproduce sound fields, we can either do simulated sound fields, or we've also done a lot of measured sound fields, particularly from concert halls. And so we'll talk about how spatial room impulse response is reproduced using the method of higher order ambisonics. There are other methods of reproduction, one of them being the spatial decomposition method and wave field synthesis, but we felt this higher order ambisonics was our first choice, and we'll talk about how that works. So here's a view of a room. This shows our direct sound coming straight from our sound source to our listener. The image in the above here shows what early reflections look like, where the sound reflects off a handful of surfaces. And eventually, after reflecting many times, we'll have late reflections. So we can measure these with a spherical microphone array, as shown in the video. And we can use the method of higher order ambisonics to reproduce our spatial sound field in the facility. Higher order ambisonics requires, on representing the spatial sound field, first encoding it from the measurement or simulation into the spherical harmonic basics functions, and then decoding it depending on your loudspeaker array geometry. So we will now talk about that in more detail. So For those unfamiliar with spherical harmonics, I'm going to take a moment to explain what they are and how it works to do this encoding process. We can begin by looking at an analogy between the time domain and the spatial domain of the Fourier series of these spherical harmonics. We can represent any sound that consists of many frequencies using a summation of cosine and sines of those frequencies with some sort of weightings applied to them. And to get a completely accurate reproduction, we would have infinite components. But depending on the degree of accuracy we need, we might use only a certain number of components and have a truncated frequency. And this is key with what we'll be doing with the spherical harmonics. So as an example, let's say our target is to reproduce a sawtooth waveform, and it consists of a number of frequencies with different weightings or magnitudes. So if we were to first represent it with just the first fundamental frequency, which is a sine wave, we would not be doing a very good job at all at reproducing this sawtooth wave. As we add now 2 of these components to get this overall reconstruction of this orange wave, you can see it is starting to look much more like a sawtooth. As we add more and more components, we're able to get a much closer reproduction of this wave using our function of sinusoids. So in a similar manner, we can do this with spatial reconstruction. And so the equation for the spherical harmonics is weighted sums of order and degree, where order goes along the top to bottom here and degree is left to right. And A n sub m is the weighting of these components. And normally based on measurements or modeling capability, we can only have a limited number of components. So let's say that this was a measured sound field that we are as our target that we're trying to reproduce, and look at how close we can get to that target using different, how many number of components in the sound field. The 0th order of a spherical harmonic is a monopole. The 2nd order, the 0th order, the 1st order components are dipoles. So if we now included the monopole and dipoles weighted appropriately, this would be the closest we would achieve to that target. If we now include up to 2nd order, we get something that's more roughly showing that shape. 3rd order, closer, 4th order, 5th order, 6th order, and we go to 7th order in this example. So if we were able to, from measurements, able to reproduce this much resolution, this would be how close we could match it. Our facility and the Eigenmike spherical microphone array that we use allows us to reproduce accurately up to 3rd order, but our sound fields usually aren't quite this complicated in spatial nature. So going back to our measured sound field, we'll be seeing more of these plots later. This is an example of looking at, this was an impulse measured in a hall. The red part of the impulse response, this is magnitude versus time. This energy was integrated, so not including the direct sound, but early reflections. And we can look at it in these plots. If you look on the right here, this gives you an idea of the measurement microphone in the middle. This is the sound energy that's coming from the front, from the left, and behind. We can take this 3-dimensional object and unwrap it like a globe as a 2-dimensional map. And you can see that there's that energy coming from the front and the right, and then quite a bit of energy coming from behind. So if we have this measured 3-dimensional sound field, we then can weight these components to reproduce this in our facility. So as a final look at that process, here's our 3-dimensional sound field, well, shown in 2D. And here's that spherical microphone array. The Eigenmike has a diameter of approximately 8 centimeters, and there's 32 half-inch microphone capsules uniformly distributed over the sphere. We can take that specific arrangement of microphones and encode what was measured into the 3rd order spherical harmonics. We then apply radial filters. These are corrections for the fact that you have the sphere taking up a space of where you're measuring, and also reflections that are scattering that's happening off the sphere. And so we apply corrections for that. Once we've done that, we can then map the appropriate weightings we need for where those 30 loudspeakers are specifically located in the facility. We apply a number of equalization filters to take into account the frequency responses of the microphone, the measurement loudspeakers that were used to take these measurements, and also the specific loudspeakers that we have in the facility. And lastly, then we can reproduce it as shown. So to summarize the facility, it is technically a hemi-anechoic chamber. We put wedges in to achieve somewhat anechoic conditions, and it allows for this reproduction of 3D sound fields using the 30 loudspeakers and 2 subwoofers. Research applications that we've been doing include concert hall acoustics, office noise, and supersonic aircraft noise. And as stated in the video, we feel this facility can be used for certainly other applications, perhaps sound quality or other ideas you might have that would allow for studying perceptual and also physiological response. This is something I didn't mention, is we do have capabilities to measure heart rate and also electrodermal activity or skin conductance, the change in salinity on fingertips in order to measure arousal level, which is associated with stress response. So I can pause now for questions about the facility, perhaps Steve, and then go on to the research applications, or would you like me to continue?
No, that's fine. Yeah. Anybody have any questions on how this is put together and the general technique? I know it is a little bit different, maybe a lot different from what other folks are doing.
So Steve, I have a real life question related to this. This is Bruce from A.O. Smith.
Yep.
Yeah, so we have a new building, and the building has an auditorium, and the sound is horrible. And I think they've worked with people to try to figure out how to improve it. But my question is more of a practical question, and the question is, are you doing analyses that are not available to a commercial person? Do you know what I'm asking, or not?
Well, I believe so. So, I mean, the analysis and work we've done, we've actually are putting together a database of our measurements that will be available soon to consultants. I think that a disconnect that often happens is the acoustical consultants know what they're doing to try and design a space, but often there's pressure from the architects to have the space look a certain way or have certain finishes that can often be a challenge to achieve the desired architectural look and what's needed for acoustic design. Acoustical consultants also don't necessarily have 3D spherical microphone arrays. And so the measurements that they can take are helpful, but they may not be able to capture everything. They do often use computer modeling though, which is helpful in determining that. So it's hard to say where things broke down. If the building was originally designed without acoustical consultants, then, and it was designed primarily by an architect, then challenges can arise that sometimes the volume wasn't sized appropriately, and then that kind of renovation cost can be prohibitive.
Okay. So I'll email you with some more questions if that's okay.
Sure.
Thanks.
Still time for a question?
Yes.
Hi, this is Filippo Fazzi from the Institute of Sound and Vibration Research in Southampton. Thank you very much, Michelle, for the presentation and for the wonderful facility that you put together. So that's really great. Actually, I have two questions, but I don't know whether you're going to answer them later. But so if that's the case, please feel free to tell me to wait until later. So one is more, if you like, financial strategical. So at the ISVR, as you might know, we also have several facilities with multi-channel audience. So, but we sometimes find it difficult to kind of have a business case to justify the, if you like, such large facilities when so much research has been now done on headphones technology. And, you know, perhaps what I'm asking here is to some advice and some help. So you were talking about industrial collaboration. So what could be, in your opinion, the main contributors or partners from the industry that could help create a good business case for a facility like this? The other question is more technical. I'll ask that later.
Great, thank you. So we've been fortunate to get funding from a company that is interested in office noise, fundamental acoustics related to that. Certainly there has been work done on that, but they're looking at it. The company is named GN Resound, and they're headquartered in Denmark. And so looking at the European market, where people have windows open, which is less common in the United States, there's concern about the amount of traffic noise that would be coming in. And so they've been supporting research to look at the effect on productivity. We also do cognitive task types exercises to see how they might be affected by the different noise conditions. That is so far our main industry support. I'm hoping that we can get further companies that might be interested in really looking at how poor open office acoustics, assuming once we move through this pandemic situation and people go back to open office environments, that I think there is a significant loss in productivity from those kinds of environments acoustically. And so I think those might be spaces. I guess sound quality, automotive industry, maybe. I mean, I know a lot of companies do that in-house, and they often use binaural heads for their reproduction, but depending on the spatial accuracy they need, maybe that's not sufficient.
Yeah, we are actually starting to hear from a few either automotive companies or companies that work with the automotive companies, and they're asking those sorts of questions because they're looking ahead to the interior of your car being, a place where you're relaxing and reading, and while the car drives you somewhere, and all of a sudden sound quality becomes a whole lot more important. Now, as Michelle said, they kind of ask questions, and then they kind of go off and do stuff on their own. But we're still hopeful that maybe one of them will sponsor some work. We'll see.
Thank you very much for the answer. If that may help, I have some collaborators in the automotive industry, and a company just told me that they created their ambisonics room. So there is certainly hope for the use of this in this kind of application. But understanding the main target now is building acoustics fundamentally.
Yes, that's correct.
For now, that's great. Thanks. If there will be time, I'm going to ask another question later.
Okay. Do we have other questions about the facility or applications to it? All right, well, perhaps I will then resume the presentation, and then we can have a second Q&A period at the end. But certainly feel free, if you have questions while I'm presenting, to do you can put them in the chat or just start speaking. All righty, just gonna move my camera out of the way. So generally, to go back to repeat in slightly simpler form, one of the first slides is the overarching theme that we do in my research group, the Sound Perception Room Acoustics Laboratory, is this general idea of what good acoustics are, the human response to it, which includes perceptual, physiological, and sometimes cognitive tasks, what metrics we can have to predict that response to then better be able to design spaces. I'll provide two updates on research that we've been doing in my group. First one is Annoyance of Mach cutoff signatures relative to common transportation sounds. This was sponsored by the Federal Aviation Administration Center of Excellence called ASCENT. And the two students, graduate students that worked on this project were Nick Ortega and Jonathan Broyles. Bit about Mach cutoff flight. So the idea with this is that we're trying to eliminate the traditional sonic boom or end wave from reaching the ground. There's strong desire from businesses to be able to travel across the country in 2.5 or 3 hours from New York to LA, as opposed to the approximately 4 or 5 hours to do so. But certainly community response would not be accepting of sonic booms. So Mach cutoff requires on atmospheric refraction or reflecting of the sonic boom wave upwards. This is a general typical temperature profile, and so the original theory was just based on a typical profile. Of course, we do not always have the typical profile, and wind has a major factor. But assuming for now in this lower region of the altitude from 0 to 20 kilometers, this is the profile that we might have. And particularly we're looking at down in this region, we have what's called the caustic line. And this is where if we have this temperature profile shown, that the end wave will come and then refract upwards with the plane applying at approximately 12 kilometers. And so a typical end wave would appear like that. The caustic would cause it to refract, and then we end up with just an evanescence wave, which sounds like thunder. And so this is, of course, if you have the correct atmospheric conditions that will allow for this, then you'll only have this remaining noise. So we did this study over a period of 3 years, and because these particular signatures had not been studied before, they do sound very different than the typical end wave. We started with a descriptor study, and this was where we had participants come in and we had them listen to a number of recordings that had been made, and on their own come up with words and definitions, and then they went back and rated all of these terms. And when we did the data analysis, these were the 3 terms. Thunderous was the most dominant, rumbly, and then something we determined swooshing, which was something to sort of the sound of like the sound crescendoing, so getting soft, starting from soft, getting loud, and then tailing off. Or crashing of waves was one participant's definition. Then what we did was, knowing these factors, thunderous, rumbly, swooshing, we then we did a study where people rated the different sounds and with the goal of trying to come up with overall metric to predict annoyance. And we found that thunderous was a really dominant factor, and that level was a strong correlating predictor of that factor. And so the third study, which is what I'll talk about today, was now that we had a pretty good idea of the underlying perceptual response to these signals, was then to look at it in an annoyance context relative to regular traffic noise that everyday exposure has. So we had recordings for all the stimuli, we used recordings rather, and so we measured at nearby interstates in the State College area. We made rail recordings of a number of different trains, no subways, and subsonic aircraft recordings at the Philadelphia International Airport and our local airport and State College. And then finally, the supersonic, we did not make these recordings. NASA made them in what they called the FAINT study. The recordings I made were made, I think, in 2011. They had 60 microphones along the ground. They had F-18s do maneuvers flying at approximately Mach 1.13 to 1.7, these heights shown here to achieve where there was no boom, but just the evanescent wave, the sound that somewhat sounds like thunder. So we first, when we were selecting various clips, we wanted 10 seconds. The sonic, the supersonic Mach cutoff signatures were approximately 10 seconds in length. And so we chose from our recordings of the rail and road and subsonic flight 10-second excerpts. And so we wanted to have 4 from each category, and we aimed to what we thought they perceptually sounded different, and then to do a more quantitative analysis, we calculated the loudness for each of the 4 stimuli, which it was difficult to have a range for the Mach cutoff signatures. And we also took a look at sharpness, so that we hopefully had a range covering these respective types of traffic noise. We presented them in AURAS. We did 3 conditions. We did an outdoor condition, which we selected as a worst case type situation. And so the road, we looked at, a number of my student Jonathan looked on just a Google map pictures and mapping out distances and finding worst case scenarios. This is an example in Atlanta of 260 feet. We had another one that was even closer. We decided to go with an average of 300 feet. We decided to make that the same for rail. And then for subsonic aircraft, in terms of distance to a typical airport, the closest, we went with 1,500 feet and then made that the same for the Mach cutoff. We then also wanted to evaluate indoor conditions. We chose a typical construction, roughly based on this exterior wall from Bradley. We made some modifications, and of course this would be region specific, so we just went with this one type of construction in our study. Lastly, we also took a level out of the equation and level equalized the recordings. We had participants do annoyance ratings, so they would hear each sound one at a time, play it, and then rate it. We also did relative preference ratings of how much they liked versus didn't like it, comparing the Mach cutoff to the other sounds. Participants, we had a target of trying to have 10 participants in each of these age categories. As you can see, it of course was easiest to recruit from the college age population. So it was difficult. We tried a number of advertising means to try and get to the higher age categories, but were unsuccessful. The target was that we'd have a 2-to-1 male-female distribution, and for whatever reason, from 41 to 70 age group, we were only able to get 1 male participant. I will show results on the next slide related to male and female preferences that is for the entire group, but we also did the analysis with just this age group to look at the male and female, and the results were the same with this even distribution. We required hearing thresholds of slightly beyond what's considered normal hearing. A normal hearing is considered 25 decibels of a hearing threshold. We extended that to 35, partly in mind of the extended age range of our usual study pool. So what we found was actually Mach cutoff, while there was lots of low frequency energy and there's certainly some infrasound, you can see was rated as lower than, oops, where my oval is. But if you look over here on the right at the Mach cutoff ratings, annoyance on the y-axis here, you can see that they are significantly lower than the other 3 types of stimuli. And you can see that the responses for outdoors versus equalized were very similar, and that we had lower annoyance ratings because the indoor ones were quiet, but we still preserved the same shape. We now look at the results across gender. So as I mentioned, these are the results across the entire pool, but we did repeat this analysis with the 18 to 30-year-olds with even male and female, and the results are essentially the same. And so you can see here that in general, that males had higher annoyance ratings than females for road, rail, and subsonic, but then when it came to Mach cutoff, there was not statistically different responses. We did see, next we look at age. Now, again, our age category is not necessarily terribly representative and uniform, and all but one of these 9 participants, 51 to 70, were, oh, actually all of these were women. And so what we see is that there is, at least with the pool we had, that the 51 to 70-year-olds rated rail as less annoying than 18 to 50-year-olds, and then we saw a swap with the Mach cutoff response. So it's hard to, we speculate that perhaps some of the older population may have grown up with rail, and it's just sort of a more comforting or pleasant sound. And we're not sure why the Mach cutoff might be more annoying for the or difference in the ratings. So even though we found that Mach cutoff is rated substantially lower than these other three types of sounds, we do think that a longer term effect and really being exposed in homes with infrasound may not bear out the same results as this controlled lab study. But in terms of individual 10-second sounds, these were the ratings. And lastly, to look at, so the preference results essentially show very similar findings, so we won't go through those. When we then did correlation metrics, so again, try and get at some numerical value about the sound that we could use to predict annoyance, these were the 5 metrics we looked at: loudness into L5, Fonz, sharpness, and then sound exposure level, which has been used extensively for sonic booms. We use 2 weightings, B weighting and E weighting. The 4 of the 5 metrics were found to significantly correlate with annoyance, and in particular, the metrics typically used for sonic booms, sound exposure levels, B and E weightings. C weighting also worked quite well. We did evaluate that as well. Were found to have the highest correlation. So moving forward, if the Federal Aviation Administration were to eventually certify this type of flight, this metric here could be a potential way to try and predict overall annoyance response. Larger community studies would be necessary to do this. And actually, back to the earlier question, there is a proposal, an initial one that has been submitted that is looking at UAVs. And so there's, I think, potential from that industry to use a facility like this for looking at annoyance response to those. So lastly, this is briefer. I'll talk a bit about the concert hall research. This was done by Matthew Neal, graduated last fall. We took spatial room impulse responses in 21 concert halls. We made some time ago a custom 3-part omnidirectional sound source, a small one similar size to the Eigenmic, about 8 centimeters in diameter, of 12 speakers for high frequency response. We use this one, I think, about 1600 to 5000 hertz. And then the dodec is similar in size to the B and K, about a 30 centimeter diameter, the medium dodec. And I think I'm sorry, it's been a while since I've looked at these numbers. I think it's down to about 100 hertz, 200 hertz. I'm sorry, I don't recall. And then we have a subwoofer, which goes down to, I believe, 80. And we use this Eigenmic, which we've discussed. And then something that we did, Matthew developed, was this additional loudspeaker, which is 20-sided. Each of these individual drivers are controlled separately. And what we did, using a database from TU Berlin and RWTH Aachen University in Aachen, they had done directional measurements, 32 microphones in a large anechoic chamber, and we were able to place our loudspeaker on these stages. We did 20 different locations, and each of those locations we would radiate the sound directional characteristics to do our sine sweep measurements with those. And to get low frequency response, we used the subwoofer. And so one of these things that we've done is we've played these auralizations back. We've created multi-channel in the facility in AURAS. We have reproduction of the 20-piece orchestra sounding spatially in front, where we combine this together. And what we do is we get people's responses, which we'll talk about briefly in a moment, and we can do a correlation analysis with the 3-dimensional sound field. So 3 categories of halls we had were fan-shaped. This particular is called vineyard or surround types halls. So this is the stage here. And then these other sections are seating sections. So they somewhat surround the stage. Vineyard comes from the name of being terraced. And lastly, we had shoebox shaped halls, our most classic shape. We had historic H there. We also had modern shoebox halls that weren't necessarily exactly a shoebox. And so we can look again at these 3-dimensional sound fields for this window after the direct sound up to 100 milliseconds. And what we're looking for, what classically is would be desirable, would be a diffuse sound field. You can see with our fan hall, we're getting some energy from the front and not much energy from the left or other directions. This is a different fan hall, and you can see that there's not even very much strong frontal energy in this same window. Looking at two surround halls or vineyard halls, and you can see different spatial. This was the one I showed earlier with strong frontal energy and really strong from behind. This other vineyard hall and the seat location, this particular, we measured in 10 to 20 seats. So these are specific seat responses. We can see low energy summed up for that period. And then when we look at a couple of our shoebox halls, we can see in this one, we have a bit more of a uniform distribution of sound, and this one with stronger reflections coming off left and right. Now this is for the early energy. We see even more diffuse responses if we were to look at this later part of the impulse response, which we won't for time's sake. So we had participants come in and they rated preference. So they were able to hear 8 different halls, and they could click between them and then rate preference relative, just like the preference for the road traffic and et cetera, environmental noise. We had them evaluate. We went through the literature and picked out what we thought were the 10 most representative attributes: brilliance, envelopment, intimacy. We separated clarity into spatial clarity and temporal, and so on. And you can see from the bolds here, the attributes that were found to be the highest correlated were proximity, spatial clarity, temporal clarity, and warmth. And so this was found to be in agreement with prominent work that was done in Finland by Tapio Loki. And we use very different methods and same to the similar conclusions. So that is just the 2 projects I will update on. No office noise this year. We'll have maybe more on that next year. So thank you.
All right, excellent. Thank you, Michelle. Got a few minutes for questions. Filippo, I think you had a technical one you were sitting on.
Oh, yes. If there is time, I'll gladly ask the question. Perhaps is more relevant to the first part of your talk, but was in relation to your recording method, the Eigen mic that you're using. And I should say it is an amazing device, really beautiful engineered and so, but as all arrays has a little bit the issue that it works very well in a given frequency range, but then low frequencies start becoming too small. And at high frequency, you start having the space in between the capsules is too large, so you have spatial aliasing. So what I find out is a little bit difficult to achieve high audio quality over a broad frequency range. And I was actually quite interested by the fact that you are really going from very, very low frequencies up to, well, the entire spectrum of the audible range. So have you devised any special solution or any strategies to optimize, if you like, or get the right trade-off, if you like, between spatial accuracy and good timbre?
Yes. So one of my past graduate students, David Dick, when we were first setting up the facility, did look at this, and I don't remember the details, but I know there were these 2 there's different ways you can do the decomposition for the ambisonic decoder. It has to do with the matrix inversion in the math. And there are different decoders available that we tried out. And one of them, the criteria they looked at, they were called the RE and the RV vector, which maybe you're familiar with. And so we did use a different optimization of which one we wanted to try and achieve: low frequency, better timbral response, and high frequency. And what I recall is that we did trade off some with the higher frequency spatial reproduction to get improved timbre, but it was still within an appropriate range for what the RV and RE vectors could be, or something like that, to still be reasonably accurate. But yes, I do recall that, and we tried several decoders that were available as VST plugins, and we definitely could hear differences in the timbral response, and so we were picking one that we thought was reasonable timbral but still spatially seemed accurate.
That's great. Thank you very much. So I understand you're pretty much satisfied with the reproduction quality you currently have, or you think there is still research to be done to improve that further, in your opinion?
Oh, yeah. So something that's been really lacking in the literature is looking at what order of ambisonics that would be sort of more of an optimal amount to achieve. My speculation is that maybe if we could move to fourth order, we might be able to. Of course, we'd have to. The Eigenmic wouldn't allow us for that, but if we had simulations that we could do, my guess is if we were able to achieve fourth order, that we would probably have a sort of our reasonable in terms of realistic how many loudspeakers sort of optimal, but there really hasn't been work as far as I'm aware that looks at comparing that the order of ambisonics to achieve that good accuracy.
Understood. Thank you very much.
All right, great. I think Siddhartha has a question. So just unmute your mic and go ahead, please.
Yep, thank you. On the annoyance results for the Mach cutoff, I think you were comparing age or gender. Well, I think it was age. Could you go back to those slides?
Yes.
You made a comment on one slide, which I have a question on.
So this is the gender results, and the next
Yeah,
slide are the age
yeah,
results.
this one. I think here you said at the Mach cutoff, they're not statistically or significantly different, but looking at the confidence intervals, that I can't tell if the male point.
Yes, I did say that. But as I was saying, I was like, well, maybe I shouldn't say it. Yes, so technically they are statistically different. So it does look like the females were slightly more annoyed than the males. But they're, yes, statistically different, but not nearly the gap we see with the other three types.
Okay, thanks.
But yes, you are correct. Thanks.
Thank
Yeah, this was like the most exciting in terms of the smallest error bars I've ever, these are standard errors of the means. They're not 95% confidence intervals, but generally when you do your post hoc test between the individual responses, if the standard error bars don't overlap, then they're normally found to be statistically different. And yes, certainly with the concert hall acoustics, we get much broader range of response, but yes, we ran it multiple times and I was like, are you sure they're this small? And yes, we are quite confident that they're tiny. So the noise resources are stimuli that I think are perhaps easier to judge. And in terms of something fairly intuitive like annoyance, when we ask people to come in and judge reverberance or clarity, we normally have musicians for that, but that's still not something that people necessarily are thinking about day to day.
Yeah, I mean, I am a little surprised that they're, I mean, like you said, you said they're not 95% confidence intervals, but I was kind of surprised they're that small given this, given the number of participants.
Yeah, it's not a huge pool of 38.
Okay, thank you.
Okay, anybody else? Great. Well, thank you again, Michelle, for the detailed look at the facility and the work that's being done. And I will point out, Michelle and I are busy working with architects on a brand new CAV area, which will include a new room for her, new transmission loss suite. It's all being built sometime in the next couple of years. So stay tuned for updates on what that new facility is going to look like.
Yes, very, very excited because we will be getting a fully isolated anechoic chamber, and yes, and I think an improved coupling between the anechoic and reverb rooms for the transmission loss testing. So.
Yep, and thank you to the College of Engineering for allowing that to happen. So
yes,
Filippo, it can happen. Just maybe some some sweet talking of the administrators is what's required. So one more today. That's the 3 o'clock student poster session. Those of you that are guests, don't worry about it. If you can't log into your Zoom account, please sign on anyway. The students will give you their updates. You just may not be able to go into the breakout room. So please join us then. Thank you again, everybody.